Oh, it's off. Okay. 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 Meanwhile, people are signing something. Okay. For those who are not signing papers, let's continue. Yeah. I hope you had a good rest. So we stopped actually with that question about rotations and translations, and I think we answered it. And now let's proceed with the topic. So now we have these homogeneous, rotation matrices, and there was this. Someone asked about the rotation and translation, which one is now included, and so on. And apparently, of course, it's all included in here. And again, a bit about the notation. This way. Again, so we have like two elements here, right? Of course, it's always like the same simple stuff. So we have a translation and we have a rotation. Just to indicate correctly what they are doing. So you see the translation vector goes from the one frame to the two frame, right? So it points from here to here. That's why it's saying 1, 2. Okay, just to remind you. But if you look at the rotation matrix, it's indicated the opposite way, right? So the rotation matrix transforms coordinates from the two frame in the one frame. So you see that the position goes this way and the rotation goes this way. So essentially what it indicates is the rotation takes coordinates from the ones expressed in the two frame to those in the one frame, whereas the position is measured from from 2 relative to 2. From the one frame to the two frame. That's the thing. And to indicate this in one homogeneous matrix, we say this is H12, and the H12 transforms point coordinates when measured in the two frame to those when measured in the one frame. Okay, that's why we have this arrow going from the source to the target. If this is the source and this is the target. Okay. Yep. Okay. Good. And again, so we kind of introduced this concept of a Lie group. Essentially, the SO3, we said the rotation matrices. There are special properties. They are orthogonal. They have the determinant 1 plus 1. And now we have the same kind of thing. So we say that all these homogeneous matrices, they're also closed with respect to multiplication, right? So if you multiply them, if you multiply such a matrix with another matrix, what do you get? You get the same structure, right? Because essentially, if you multiply, do we have it somewhere? Yeah. If you multiply R1, 2, for example, with this vector here, with R2, 3, with this vector, what you get is the rotation matrices multiplied, and then you get a vector here. Whatever it is, it's simply the displacement propagation. But what it indicates, what it means is that whatever you do here, again, you get the rotation matrix. Okay, so again, you get a matrix that is an SO3 matrix. And here you get a 3 vector, whatever vector, but you get a 3 vector. So the form of the matrix that you're getting is always invariant, okay? Which means that, again, these matrices, I mean, these homogeneous matrices, they are closed in a sense. You multiply them, and you always get a matrix with the same structure, okay? And also there's an inverse, and the inverse apparently is a 4 times 4 matrix, identity matrix. That's clear, because it's a matrix. And there's a clear inverse. So they are closed. We have an identity, and there's an inverse. There's always an inverse because they are regular matrices. I mean, the rotation matrix is an orthogonal matrix. There's the one, so you know exactly that this certainly has an inverse. And as you just said before we went to lunch, the closed form of the inverse is exactly this one, right? So you can just check it, multiply this with this, and you see that you get the identity matrix. So there's a unique inverse, okay? And this makes, again, the whole set of these matrices into a group. And for some reason, we call it the Lie group. And then we will see why, later on, we will see why we call it the Lie group. Anyway, it's a group. By definition, it's closed under this multiplication, and it has an inverse and an identity. Okay, yeah. So just what I just mentioned here. If you have two, I mean, you can combine them. You can concatenate, of course, the transformation from multiple frames. So, for example, from 3 to 2 to 2 to 1. Of course, I mean, this is the pure logic. Of course, I mean, you just combine them. What's important again is that they match, right? That the indices match. 2 must be here. So what comes out here has to go in here, and altogether the 3 goes in and the 1 goes out. Okay. So you have a homogeneous transformation matrix that transforms coordinates, I mean, point coordinates from this 3 frame to the 1 frame. Okay. And of course, you can do this in any other, arbitrary order and so on. Okay. So this is it. This is all about, you have to know about this homogeneous matrices for the time being. Of course, there's a bit more, and that has to do with the question, how do you coordinate them? I mean, what kind of parameters are you using to parameterize them? So we heard about this Dennard-Hartenberg parameters, if you know them. Yeah, they are okay, but they are not. First of all, they're not unique, and secondly, it's a Dennard-Hartenberg convention, the DH convention, in a sense. You have to strictly follow certain introduction of frames and coordinates and so on, and that's not easy to do. I mean, easy to handle because it's a bit of a headache, and also it's not flexible in a sense that you are really have to follow this, and that might not be a good idea to follow this kind of procedure. And what's the alternative? The alternative is exactly this. There was a question: what's the benefit of the screw? Where's it now? Yeah, screw theory, and that's the alternative, which is, I guess, better. Before going there, we need some other mathematical kind of tool, which is to any matrix. To any vector. Let's stick with the 3 vectors. To any 3 vector components, maybe A, whatever, you can associate a skew-symmetric matrix. Okay. So you know what a skew-symmetric matrix is? Do you? Oh, okay. So essentially, the matrix is skew-symmetric if you take a transpose, and what comes out is a negative matrix. And if you transpose this guy here, apparently you get a negative, right? Because this goes here, and this goes there. And for any, of course, skew-symmetric matrix, this must have the zeros on the diagonal, otherwise, because this element must be equal to itself. This element must be equal to the negative of itself, and this can only be a 0. Yeah, the notation is as follows. We have this tilde, this curly thing on top of it. So we indicate when we take a vector, and then we have this we call it tilde operator on top. Then this is the matrix that comes out, the skew-symmetric matrix that comes out of the vector. Right. So that's it. There's a property because this you find this also under the name of the cross product matrix. Do we have it somewhere? Yeah. It's sometimes called the cross product matrix or spin tensor. Simply because if you take this, where's it now here? If you take A tilde times B, right? It's the same like A cross B. So it's essentially a different way of writing the cross product. But this A tilde has its own life, right? It's independent of performing cross products or not. We have this matrix, and we will use this matrix for different purposes. Okay? Clear so far? So good. Okay. If you have time tonight, you can try to choose to show that if you take a rotation and multiply it with a vector, any vector, it's the same as if you and the outcome, you plug the outcome into this skew-symmetric matrix. It's the same as if you take the skew-symmetric matrix of that vector and then left multiply with R and right multiply with the rotation matrix. Yeah, you can try to show this. Okay. Oh yeah, that was it. So what about parameters? How do you describe rotations, spatial rotations? And there are different ways of doing it. I guess you have learned about like Euler angles, like 3 angles that you combine. Yeah, one way of doing it. But what if I would like to have the rotation matrix that is actually describing the rotation about the given axis? So I give you an axis, maybe a vector along the axis, and I would like to have the rotation matrix that describes the rotation about that particular axis. The three-angle description doesn't really help you, right? Mm-hmm. What is this?
A cylindrical coordinate system in which if there's a rotating body, it must have a cylindrical structure, right, when it's rotating. So we can mark the points and then convert it into an array or like.
Okay, yeah, sounds like an interesting, maybe complicated way of doing it. Yeah, quaternion, of course. Yeah, good quaternions. Yeah. Actually, what we're going to do is mostly the same, more or less the same as using quaternions. How do you get quaternions? You need the vector and you need the angle, right? And then you have a formula, and that formula is actually an exponential of the quaternions. Okay, maybe when we finish, we can talk about the connection to what we're seeing here. Anyway, there is a famous theorem. It's the Euler, many Euler theorems, I guess. But there's one theorem by Euler about the finite rotation. And what Euler said is, and it sounds easy, but it's not that easy to prove actually, that any finite rotation can be achieved by rotation by the constant axis. So what he's saying is that, I mean, you take any, whatever kind, you take a body, right, this one, and you take another, yeah, exactly. So from here to here, there's always a constant rotation axis so that you can rotate about that axis and you get from here to here. Well, this sounds easy, right? But what about this? I don't know, like this. So what's the axis? That might not be that easy. Or what about this one? Yeah, it's not always obvious, right? But it's always possible, okay? Okay, this is a theorem. By the way, this is saying that from here to here, there's one constant axis. So there's a constant axis. I mean, this is a simple example. Probably the axis is over here, and then you do like this, right? Okay. This is kind of helping you if you want to go from one pose to the other. But if a body like this one is moving in space, I mean, continuously, then the question is, okay, what is actually the instantaneous rotation axis? Because this is not the one that Euler was saying. Because Euler was saying, if I want to go from here to here, there's a constant axis. So essentially, it goes like this. But I have no idea how this bottle is, came from here to here. So it might be totally different. And that's why there is a different theorem that's normally associated to Mozzi-Cauchy. And it says that, the same essentially, that for any spatial rotation, there exists, and is important, an instantaneous rotation axis, right? It's maybe not so kind of surprising because there should be a rotation axis, but proving this is not that easy. Anyway, because of this, we can actually do a bit of mathematics, and which I'm skipping because we have no time. But anyway, essentially the ingredient is a unit. You take a unit vector, call it E, along the rotation axis. So let's say you have a rotation axis. This could be an instantaneous rotation axis or just finite. It doesn't matter. So you have an axis about which you want to rotate, okay, and a certain angle, phi, okay. Now what we're doing, we plug this unit vector into this Kinematics matrix. Okay, that's done. And then I claim that this is essential. So the rotation matrix that performs the rotation in question is the one that you get when you plug this the matrix E tilde times phi, which is the 3 times 3 squeeze-symmetric matrix, into an exponential. So what is the exponential? I mean, the exponential, you know this. I mean, there's a Taylor expansion for an exponential, right? So you know the scalar exponential function, right? So it's essentially, it's like it's 1 plus, if you have a scalar, like the exponential of x, for example, it's 1 plus x square half plus 1 divided by the 3 factorial x to the power 3, and so on and so on. Symbolically, you can do the same. I mean, this is mathematically proven. I mean, you can do the same with matrices, right? You do in system theory, when you solve linear differential equation, for example, then you do more or less the same, right? So whatever, you can plug this into the exponential, and the definition is the same. So you take the power of 0, the power of e tilde to the power of 0, which is the identity, plus this guy to the power of 1, plus this guy to the power of 2, divided by the 2 factorial, and so on and so on. Okay, that's nice, but how does it help us? The thing is, if you... I skipped this actually on the slide, but maybe you have time tonight. What's the square root, the square of e tilde? If you take e tilde square, what do you get? Yeah, that's not a good question. I should stop here. You get something. But what if you take the e tilde to the power of 3? Sorry. That's the point. If you take so if you take what was it then? So if you take e tilde square, you get something that you can't change. You can multiply it out, you get something. But the thing is, now if you take e tilde to the power of 3, what you're actually getting is e tilde again. And that's something interesting. Multiplied with the norm of e squared. And I have to correct myself because this is minus. Okay? And that's the key. That's the key. Of course, we know now this is actually a unit vector. Yeah, okay. But I have to say that we're multiplying, of course, this guy multiplied with phi. That's why we have actually phi to the power of whatever we have here. Anyway, but the e itself is like this. So why is it the key? Why is this so helpful? Simply because now you have all the powers, right? If you have, you have the power of 4, then it's the same. I mean, I can't do anything. I mean, e squared is e squared, whatever. But the point is that the power of 3 boils down to e itself. Now, of course, e5, right? If you take to the power of 5, that's clear because you have this scalar minus the norm squared times, and this becomes e tilde to the power of 3. The power of 3 is this one. So essentially, it's plus e to the power of 4 times e tilde, right? And it goes on like this. So essentially, you're ending up with e tilde and e tilde squared. The only thing is that you're summing up these scalars here with an alternating factor, alternating sign, plus minus sign. And this is what you see here. Because now if you collect whatever comes into e tilde square, then you get this. Okay, then you get this, these series. Now question, have you seen them? Someone has seen them, but you're not supposed to say anything. Okay, what's the Taylor expansion of sine and cosine? It's always the same. Okay, this apparently only has odd powers, and this only has even powers, right? So, which one? So sine is an is an odd function, right? You know, even an odd function. So the one is. Anyway, I'm telling you, this is the Taylor expansion of the sine of phi, and that's almost. It's actually 1 minus cosine. Because the cosine is 1 minus this term plus this term minus this term and so on. So it's essentially 1 minus cosine, and that's it. So by using this claim, so to say, which I didn't prove, that this is the case, we find a closed form expression for the rotation matrix that performs the rotation about the unit vector e and an angle phi. And that's pretty simple, right? Okay. And that's essentially the Euler-Rodriguez formula that you find in the literature. Okay. And that answers more or less the question. So what is the rotation matrix? For that, we have it. Sometimes because now you have two ingredients here. You have e and phi. You have a unit vector and phi. You may say, okay, why don't I just, call this E times phi? I call it psi, for example, whatever, like this, right? Then it's the same. You just plug in instead of E times phi, you have psi. And then it comes like this. Of course, you have to have a unit vector here. You have to divide by the norm of this. And then in the end, you get the same. You get this. Okay, so there are two versions of the same thing. Yeah, so, and by the way, this is normally called the scaled rotation axis because it's just as you say, the angle times the unit vector. That's it, full stop. I mean, this is the famous Euler-Rodriguez formula, and that's it. The E bar, which one? You mean this tilde? No. Oh yeah, that's here, this one. So what it is, yeah, it's the unit vector, it says here, it's the unit vector along the rotation axis. So the E, so the question was, what is the rotation matrix that describes the rotation about a certain given axis and an angle? Now, we have two ingredients here. First is of course the angle, and then we have a unit vector along the axis, and the unit vector is E, right? The what? This one here? That was what we had in the, no, sorry, wrong direction. That's what we had in the, just in the slide before. Here. So you take this, now here was A, right? Now you take any vector. Now E is E1, 2, 3, and it goes in here. So this is this Q-symmetric matrix that you associate to a vector, and that's called E. I mean, a vector now. And yeah, and it's important. I mean, this is an important kind of relation. There's a one-to-one correspondence between a skew-symmetric matrix and the vector. I mean, once you have the skew-symmetric matrix, you can always take out the, this is minus the 3 component of the vector. This is plus the 2 component. This is minus the 1 component. You always can take them out and plug them into the vector again. And you can do the opposite and just taking this and plug it in here. It's, again, a different kind of bookkeeping, just the same numbers in a matrix now. But the good thing is that this matrix is actually allowing you, for example, to express the cross product. If A cross B, then it's A tilde B, which is nice, but it's not important to us because for our formula, the only ingredient that we need, or the only reason for using it, is because if you take this E tilde, this Q-symmetric matrix, where it just goes in the unit vector along the rotation axis, we get the Euler-Rodriguez formula. And in the end, I mean, you just take this maybe as a recipe, or maybe the next slide, because, yeah, that shouldn't be here. Anyway, as a recipe, for example. So when you want to have compute the rotation matrix, you compute this. The only thing you have to do, well, identity matrix, then you have this E tilde, this Q-symmetric matrix, and then you have to take the square root of the Q-symmetric matrix, and that's all you have to do. Yeah, and as you saw, there are different ways of doing it. I mean, different depends on the input that you get. If you get just that vector multiplied, I mean, if you could just get a vector, whatever it is, call it C, then the rotation matrix goes like this, and that vector would come from the axis and the angle by just multiplying the axis with the unit axis with the angle phi. And here it's separated because if you have explicitly the unit axis and the angle phi, then you use this formula. And by the way, I mean, if you can also, if you have this, you can also use this one. If you have the vector, you divide it by the norm, because the norm of this vector is equal to phi, right? So the norm of phi is equal to phi, to the angle, because this is a unit vector, right? So you could easily introduce E as this vector divided by its norm, and then you have the same that you have here. Is it somehow clear what I'm talking about? So essentially, you have two ways of actually using the Euler-Rodriguez formula. The simple maybe, I don't know, simplest one, maybe it's this one, angle and vector. And then there's this one where you have a general kind of vector given. Somewhere, someone gives you the vector and says, I need the Rodriguez formula, then you can use this. There's a bit of a problem because, why? Because here dividing by the norm. Now, if C becomes 0, right? If this tends to be 0, for example, if you have the angle 0, I mean, if no rotation, for example, right? Then you're ending up with this vector being 0. That's not a problem because you divide sine of this number divided by the number. So the limit exists. But if you are going to implement this is going to be very difficult. I mean, this gives you some headache and some artifact. Because what you would have to do, what you normally do is you say, okay, if this is less than 10 to the minus, I don't know what, 7, 8 or so, then you say, okay, then we use, what is it then? What are we using? What do we get if you multiply this? Okay. What's the limit? If you take this guy with the norm to go to 0, it's equal 1. Because this is known as the cardinal sign, right? In system theory, this is this function that looks like this thing, okay? Okay, this goes to 1. What about that guy here? That goes to... Huh? That goes to... This goes to 0. That's right. So this goes to 0. But you have to look at this guy here. And if this goes to 0 quadratically, this goes also to 0 quadratically. So it converges to 1. So the whole thing converges to 0. This goes to 1, this goes to 0, and it goes away. So this converges to 1, as you said, which is correct. This becomes 0, so the whole thing becomes 0. And of course, for the angle being 0, then you get the identity matrix. Anyway, if you implement this, you will have to have like if and then, right? So if this is less than this and that, and then you have this artificial kind of switches. And this is never good for numerical implementations. That's why you should use this sign, this cardinal sign. You find this in all computer programs, if you look for it. Actually, sign C is just defined as this. We have to be careful, by the way, in MATLAB. I guess you use MATLAB. This is ridiculously implemented. For some reason, I guess I don't know why. Maybe it's because they're focusing on signal processing. This is implemented as the sign of 2 pi times the argument divided by the argument. It's a bit strange. Anyway, it's just a factor. But you have to be careful when you use MATLAB. Okay, good. So this, as I was saying, this has a problem with the singularity, but that is, of course, robust. I mean, this one is a robust one. And of course, if you have phi and phi and e just separated, then there's no problem at all. This is all okay. The only thing is, of course, there is no unique rotation axis for phi equals 0. Because if the angle becomes 0, then e could be arbitrary, which is okay, right? I mean, no rotation about any axis is the same as, I don't know, as no rotation about a given axis. Because no rotation remains no rotation, right? Yeah, okay. This so far, I hope this makes some sense to you. Does it? If not, we have to do something. Okay. I take this as a no. I take this as a no, which means that we maybe should have a bit of a look. So you can easily implement all the stuff, right? And of course, we did it. Yeah, I don't know. If I share my screen, then it becomes a bit smaller. Maybe increase it a bit. So essentially what you have here is an implementation, right? What it says is, yeah, and we said that, so this was an exponential. And we said that what comes out is a matrix, is a rotation matrix, which is in what we call SO3, right? So in the special orthogonal group. Anyway, so, and this means that it's an exponential for rotation matrices, for elements of SO3. It's just a naming. So And I use here because, I don't know, because I use it for many, many years. I use also MATLAB, but I show it in Mathematica. I'm not sure if you use Mathematica. Yeah, you? Anyone else? Mathematica? No. It's quite powerful software. It's a symbolic, it's like Maple. Maple, Mathematica, they're competitors. Anyway, so essentially what it shows here is exactly what I told you. So this is it. And that's it. So, and maybe let's try to, I don't know, to do something. Let's have a unit vector. Yeah, we have to, which one? I don't know. Okay, where are we? Where's this? Here. Where's it? Where's the function? Ah, here. Okay, so we use this function and we say, for example, take the exponential of, for example, E1. So when I say E1, this is just the unit vector along the x-axis, right? So the components is x, y, z. Oh, actually, no, this is the z component, of course. So it's x, y, z, okay? And apparently it's a unit vector. Okay, maybe do like this so that you see. So this is what comes out. And if you like, you can also have the angle, if you like phi better. So that's it. You could maybe have a look into what really happens here. What really happens here? For example, this skew symmetric. Where is it going? Here. For example, this skew symmetric matrix. Because we can stick here. Okay. So I call this axis to little SO3. Essentially, it's the tilde matrix. We come back to this when we talk about this. Why the naming? So anyway, this gives you the skew symmetric matrix out of vector. Let's use E1 again. Then you get this. And maybe have a look at the. So this is what you're getting. And maybe we could make this a bit more explicit. Let's say E1, E2, and E3. So, and this is what you get. E3 was not a good idea. Okay, let's use A. A1, A2, A3. So this was the definition, right? It just implements the definition. Now the question was, what is it if you take this squared? That is actually the answer. So this is what you get when you take the square root of this. Just the square of this. And yeah, I mean, there's not much more to say. So you take this one. I mean, this is the formula. You take this, the square of this. By the way, the dot is the matrix multiplication. Times 1 minus cosine, and that's it. And then you take the sine times the skew symmetric matrix. Yeah, that's it. I don't know what we else can say. Maybe let's have a look at this. What I claimed, this square root property. So now, okay, let's say A2. So this is A squared. Okay. What about A to the power of 3? This is, of course, A squared times the A again. Okay. And maybe do like this. So A3. So this is what you get. Maybe we should simplify it. So, and I guess you see what I was claiming. Because essentially what you see, compare this, for example, with this guy. So this is A tilde. So this is the skew symmetric matrix that you get when you plug in the vector A with A 1, 2, 3 component. Now this is A to the power of 3. So what do you see? You see exactly here we have, here we have A3, which is the negative of this part. Then here we have minus A2, of course, which is the negative of this. And here we have plus A1, which is, of course, the negative of this thing. And they're all multiplied with the norm squared, right? So this was what I was saying. And this is all you need to know. because then everything follows immediately by saying, okay, power 4, power 5, and so on. Okay. I'm not sure if you're convinced now, but if you have questions, then okay. What about the quaternion? How do you construct quaternions? Mm-hmm. And how do you get the scalar factor? How do you call it, the imaginary part and the scalar part? So essentially, this, I mean, it's very much the same, because you construct them actually with an exponential. You construct them with an exponential of the vector quaternion, right? Okay, so your quaternion, how do you call them? Like Q or something? Uh-huh. And so it has got the scalar part. How do you call this? S. Ah, okay. Do like this. Yeah. So what's the scalar part? You say D. Okay. So plus. Oh, ABC. Ah, I see. ABC. Okay. So A times I don't know how to write this. B times, I guess, J, right? And C times K. I don't know how to write this here, these things. Yeah. Okay. And how do you? You can also. Yeah. This is kind of so the. Who knows quaternions? You're the only one. So it makes not much sense to talk about it, I guess. Anyway, so these are the. What is this IJK? The Hamilton basis, so to say, right? Yeah. You can also write it like you call it D, and then you have a vector. Yeah. Oh, not easy. Not easy. Let's call it Q. We call it. I mean, everybody has a different notation, right? Q0, and then we have Q vector. And the Q vector is essentially ABC for you components. And now the Q vector is, so how do you get it? If you have a rotation axis and a unit axis and an angle. So again, if you have a unit axis and we have a rotation angle, then you get Q as the vector times sine of what? Yeah, okay, like this. And what about Q0, which is your D? It's the cosine of phi half. And this you get actually by, as very similar, actually it's the same formula, Rodriguez formula, y an exponential, but let's not go into this. Okay, so why is it good? I mean, why is it better than rotation matrices? Why do you use quaternions? Yeah, but you have to explain what singularity means. For that particular parameterization that you mentioned. Because, I mean, if you have, where's the singularity here, for example? Do we have a singularity? Yeah, we do. I mean, at least we have some indication for a singularity. Yeah, maybe it's not, because this is not for the rest of the audience. But what you mentioned, gimbal lock, for example, right, is when one of the angles is 0. And that happens for any, so what you're using is like a 3-angle parameterization of spatial rotations. And any 3-angle parameterization has singularities. So any, right? Okay. Yeah, any has singularities. And the question is now, what about this one? Do we have singularities too or not? And the only one is this one, but this is not a problem because we can solve it. So the singularity problem is not necessarily here an issue. Okay, good. Yet, maybe it's not really clear what the rotation matrix does, because at the beginning we have been saying that the rotation matrix has to have indices, because the rotation matrix transforms from one frame to the next frame. I don't see from where to where this matrix goes here. It doesn't give me any indication. I mean, what I know, this is a rotation matrix, but I don't know what it does. Not yet, at least. And that is easily done. So what you see, I mean, what you find out when you do a bit of mathematics is that you get actually, you have two frames, 2, 1. And we are looking for, I forget about the comma here. We look for the rotation matrix that goes from the frame 2 to the frame 1. And there we go. Yes, frame 1 to, yeah. So, and I would postulate that the rotation matrix that you get from the Euler-Rodriguez formula, when you plug in the unit vector about the rotation axis, which is some unit vector, I don't know, some unit vector here, and expressed in the one frame. So what I'm saying is that essentially, if you want to have the rotation matrix that transforms from F2 to F1, where F2 is actually the result of a rotation about a certain axis of the frame 1, then this is the rotation matrix that is giving you this transformation. What happens if you have, as I was saying, I mean, phi equal 1, which is what? Identity matrix, which is no rotation. No rotation means that F1 and F2 are overlapping. They're essentially the same, right? So I could actually skip this this second body here. I can actually skip it because it's one and the same body. It's just the one, this one is the copy, so to say, after the rotation, right? Having said this, I know exactly that actually F1 and F2 are the same at the very beginning. And I know that what I'm describing here is essentially the motion of F2 relative to its initial pose, okay? And then the question, there's actually, so you should have asked maybe, in which frame is actually the vector E expressed? Because at the beginning I was saying, okay, we have a vector. Okay, good. But in which frame is this vector expressed? And the answer is pretty straightforward here, because the vector, if you believe me and if you follow me, then we don't need S body 2, because we have only one body that is moving, right? This is just a snapshot after the motion. So the question, there's no question, because you only have one frame. This is F1. There's only one frame. So what you're describing here is the motion of the one and only frame 1 because of the rotation about the axis E and the angle phi. And what you use is the Euler-Rodriguez formula. You measure, you express the rotation axis in the frame of which you are interested in, that is rotating, and plug it in here. That's it. And you get out the transformation, and this is indicated here, that transforms from the displaced frame back to the original. And that's an important understanding, because many people, in many textbooks, you get confused because they don't say anything. There's just a rotation matrix, but then what is it doing, right? And that's an important point. You can close your eyes. Essentially, when you know in which frame this vector is expressed, then you know exactly what this is doing, because it transforms from the displaced to the original one, right? Of course, we are interested in the relative rotation, or relative motion of two frames, of course, right? And the two frames that we are interested in are just, so to say, copies of the same frame after a certain motion, okay? That's why we do numbering, and that's why we are using this to represent the motion of two frames, so to say. But remember, it's the vector that describes the rotation is always expressed in the target frame. That's why it has to match. So the vector is expressed exactly in the target frame. So they must be the same, always. Otherwise, it doesn't make sense. Yeah, that's it. Yeah, this is for people who are, yeah, that's just a reminder. So this is the Euler-Rodriguez formula for you. Yes, and then you mentioned gimbal lock, and you mentioned, I don't know what you mentioned. I mean, combining combining one-dimensional rotations to get three-dimensional rotations out of this, right? And this is what you do by saying, okay, let's say let's say I'm constructing a 3D rotation by rotating, for example, about x, then y, then z. The good old, I mean, the original Euler formula was the so to say, the Euler convention was rotating about the z-axis, then about the x-axis, the z-axis, then the x-axis, and then the z-axis again. But now in the literature, I mean, this was what originally Euler was actually saying. But in literature, now you find different versions of Euler angles. Yeah, they're just angles. They're not Euler angles. But the point is, whatever you do is correct because you can combine all combinations. I mean, you can rotate about x, y, and z, or z, y, and x, or y, I don't know, z and x. It's up to you. The only thing you have to remember, you of course, you cannot combine two successive rotations should not be about the same axis, right? You cannot rotate about x, and then z, because this is not giving you a spatial rotation. And also the important point is that any of these three parametric parameterizations have singularities, as you said, and the gimbal lock is one example. And essentially what you do, you combine these elementary rotations, because if you rotate about the x-axis, you have the one. So these are the unit vectors about the axis we are rotating. And let's say that we are rotating about the x-axis. By the way, there's different numbering. So the frame is, the axes are called x, y, z, or 1, 2, 3. I like actually 1, 2, 3, but anyway, it's nicer to say 1, 2, 3 instead of x, y, z. Anyway, this is the x rotation, y rotation, z rotation. And that's it. So you plug in this, the unit vector about the x-axis, and then you get out this. We can try again, but this is, of course, clear. And the same with the y-axis and the z-axis. How do you see, I mean, how do you recognize which axis you are rotating about? Yeah, you look at the ones, right, here. Yeah, and okay. What's the, okay, so how to ask? I don't know how to ask. I was about asking, how do you see this? And if you see it by multiplying this matrix with this vector. Because this vector is invariant, right? It's actually an eigenvector of the matrix, right? And of course, this is by definition. The vector that is invariant under a rotation is the rotation axis. Because the only points that are not translated or moved in any way are the points on the axis. And that's exactly what it says here, because if you multiply this, you get the same vector out of this. Yep. Okay. And then you can combine them. Exactly. So, and there's, yeah. So you said, so you had some objections, as I remember. No, I'm just kidding. You had some objections, right? When I said z, x, z.
Some convention says like that from z rotation we go to y rotation and then x rotation.
So z, y, x.
We are doing that rotation.
That is also a good thing. This is called the Cardan angle parameterization or Bryant angle parameterization. Anyway, it's just the names are a bit of hazy now, but originally Euler was doing the other way. Anyway, this is good. So let's maybe stick with this Euler param. I mean, it's the same. The derivations are the same, but the old Euler angle parameterization is the one where you translate about rotate about the z-axis, followed by a rotation about the x-axis, followed by a rotation about the z-axis again. Let's see how this goes. So let's say this is our space 6 frame. Okay, And then we are doing the first rotation, which is, what is it? No, this is nothing. This is the final one. So actually, I want to go from here to here, or the other way around. Anyway, this is this basics frame, and this is the body frame. So, and the question is, how do I get from one to the other? So the thing is, how you construct, and this is a nice old construction. How do you construct Euler angles? And the Euler angles, or let's say the Euler construction, beyond Euler angles, has a nice implication. It comes from celestial mechanics and so on. What you do is you look at the plane. First of all, look at the xy plane of the space fixed frame, the black one. And then you just construct the xy plane of the moving frame. And I just took a circular, cutout because the plane is infinite. Okay, they're intersecting, right? So they're intersecting at one line. This is the knot line, it's called. And that's unique unless, and this is the gimbal lock. No, this is the singularity, not the gimbal lock in this case. Because if they are this, if this would be only turned about the horizontal vertical axis, right, then they would not intersect in a line because the planes would be the same. Anyway, so let's say that we are in a general case. So we have a knot line here, so they're intersecting, okay? And now you can introduce, or you can identify certain parameters to describe this situation. And you need 3 parameters. So let's say you measure, for example, the angle between the angle in the xy plane of the space fixed frame, the black, the gray frame. So you measure the angle of the knot line relative to the x-axis of the space fixed frame. Done. Then you measure the kind of inclination of the xy, the red one in the moving frame plane. And this is essentially saying that you measure the angle between the 2 z-axes. This tells you how much you're actually, tilting this one. And then you measure, you can measure before, but anyway, and then you also measure the angle between the knot line from the to the x-axis of the moving frame in the moving xy plane, right? So essentially, you have 2 planes. There's a knot line. Then you measure the angle between the x-axis here and the x-axis in this plane, and then you now have to say how much the planes are tilted, and that's the theta. And this together gives you exactly the Euler angles, because the psi, theta, and phi, these are the Euler angles, and the rotation goes like this. First, that one, so you rotate about the z-axis. Then you rotate about this one, which is that one. This is the x-axis, because you rotate about this x-axis. And then you rotate about this phi, which is here, which is again about the... this one, about the z-axis, the new z-axis. So you rotate about this axis, that axis, and this axis, okay? And they are called precession, nutation, and rotation. And you might have, you don't need the planes actually. You might have heard, you might have heard of this when you worked, I don't know, when you had a physics course, or if anyone is in space mechanics or so, because this was what Euler actually did in a, anyway, this is not important. Because he was looking at the motion of a heavy top, or let's say our Earth actually, because the gyroscopic position things, exactly. So when you have a heavy top, did you play with this kind of things? Is it, okay, you did? Anyone else? Like you spin this thing and then you... so he was interested in, I don't know if he was interested in, but actually what he worked on was actually considering this for the rotation of our Earth, right? Because the Earth does the same. The Earth, or let's say the gyroscope, or let's the heavy top, we call it. So this thing is rotating, right? So there's a rotation axis. So the big rotation, the spinning goes like this, about this axis, okay? And then what it does actually, it does spin it around. It does, what is it doing? Yeah, so it is rotating about this, with a high speed, for example, right? So this is where you start it, and it does like this. And then you might actually kick it a bit. It doesn't fall down. It just starts to wobbling around, right? And what happens is that the rotation axis is actually starting to do some circular motion about the original vertical axis. What else do we have? That is exactly. So this is the rotation. This motion is called the precession. And the nutation is the one that is actually going back and forth. Because what I should have a picture maybe. So this is rotating with a high speed about this axis, right? And then the axis itself is rotating about the vertical axis. But it's not just rotating, it's doing like this, back and forth rotation. So you have the three components. And the last one is called the nutation. And if you look at the Earth, for example, then you can see this clearly, that our Earth is actually doing this. Now you can say, okay, how long does it take for one rotation about this? 24 hours, right? The other thing is, how long does it take to for one position? Huh? No. This is the point. It takes much longer. It's a 30,000 years or something like this. And it's changing because everything is changing in the universe. Yeah, okay, so this is it. So this is the Euler angles. And the singularity, gimbal log is one example. In this case, the singularity happens when this angle is 0. Why? Because you simply cannot distinguish, maybe go back to this one, because simply you cannot distinguish. If this is 0, you cannot distinguish this one as rotations, which is the Bryant or Cardan angle compensation. Then you have the singularity when the middle angle is 90 degrees, right? So, and there's a theorem, and you can not easily, but you can prove it. Any three-parametric parameterization has singularities. Whenever you use three angles, there's a singularity. That's why people use these quaternions, because you have 4 parameters, but they're not independent. Okay, good. Not sure if we should maybe. Yeah, as I was saying, there are other things we didn't talk about it. Maybe the message is when you use other parameterizations, like this is what you are using, then for the same rotation, you get different angles because the combination is different. So whenever someone gives you 3 angles, you have to really ask what they mean, right? Okay, good. What about the spatial motions? What about this kind of thing? Because so far we looked at rotations about an axis. What about the displacement? I mean, the translation. That's what concerns the screws, the screw theory. Exactly. Yeah. Okay. Do you have questions so far? If not, then let's actually go to this. So we have seen this Euler theorem. I mean, the Euler and the Cauchy-Mozzi theorem. That was saying that there is an instantaneous rotation axis and a finite rotation axis, right? Okay, this is only about rotations. What about if I have a full body, I mean, a full 3D motion? Yeah, it's different, right? But there's again an interesting statement that goes back to Charles. Actually, there's again another thing. Maybe this one. This is the full Mozzi-Cauchy theorem. So Charles was actually proving and stating. Come on. Stating and proving that any rigid body displacement can be achieved by a screw motion. So what is a screw motion? I mean, everybody knows a screw, right? So what is the property of a screw? Maybe I should get off this. What are properties of screws? Okay, what is a screw? Silly question, right? So a screw is defined by an axis, right? I mean, literally, you have a screw and you turn it and it does something, right? And that's called a screw motion. So you have you have a well-defined, so to say, again, axis of the screw axis. Now, when you do motion, I mean, when you do the screw motion, then you rotate about this axis, right? So you rotate somehow, But you also translate along this screw. And yes, that's nice. Now, if you're sitting somewhere, so let's say you're sitting here, right? And this thing is rigidly attached to your screw axis. Or let's say to your screw, I don't know, to your screw. So what I'm actually about to say, if you're sitting here, what happens? The thing is actually doing a screw motion. So it does like this, right? So, and this funny motion is the most general rigid body motion. And the claim is that every body or every motion of a rigid body is a screw motion. Okay. What are properties of screws? One was the axis, right? Let's call it E again. And there's something, for some reason, they call it H for helicoidality or something like this. Like how much is it a helix? The pitch, exactly. So H is the pitch. So pitch is between 0 and infinite. Infinite, yeah. Infinity. Oh, God. What if H is 0? There's no translation. So when you're rotating about your screw, you're just rotating. There's no translation. This would be a pure rotation, right? And now think in terms of joints, because this is what we're going to look at. A revolute joint is a zero pitch screw joint, so to say. If you have a proper screw joint, then it has a certain finite pitch. You rotate it, and What about a prismatic joint? A pure translational joint? Zero rotation. What is the pitch? It cannot be finite. It's essentially, I mean, this is not easy to explain at the on the spot. It's infinite. You can. So, what's the pitch saying? The pitch says how much you translate per rotation. You can also put the other way around. It's 1 over the, what is it then? Rotation. How much rotation do you need for unit translation? Now, if you go to the limit, you can say, well, I need an infinite rotation to get what? What was I saying? Yeah, infinite rotation to get a finite translation. Anyway, this is more like a symbolic assignment. You just say for a pure translation, the pitch is infinite. It's just okay. What else? Yeah. So do you believe it? I mean, the thing is, I mean, I give you, I don't know what. I give you 2 objects. What's the screw motion from here to here? Huh? Yeah, that was a pure translation, yeah. What about, I don't know, what about this one? Yeah, from here to here, you just do like this, right? Okay, you say like this. Is this what you say? Okay, but okay, what is the screw motion? There's one screw axis, so you translate along the axis and you rotate about the axis. Which one? Okay, so where's the, so first, so these are the 2 things. So from here to here, or the other way around. So how do I get from there to there? Along one single unique screw axis. But I have to combine, translation with along a line with the rotation about the line. It's pretty simple. Yeah, you mean like this? Yeah, exactly. So the screw axis is between here and here, and then the motion is which one? That's the translation, right? So you do like this. But there are more complicated situations where it's not that easy actually to find easily the screw axis. But any motion can be achieved at least by rotation, by screw motion. Yeah, and there's of course the Mozzi-Cauchy theorem that says at any instant of time, because again, I have no idea how this came to here, right? It kind of gone through the whole universe and then came here. And there's an instantaneous screw axis that does it. That does the job. Okay, how does it help us? Now again, no, not again. This is just pure kind of reasoning. I would like to have the rotation, the homogeneous transformation matrix. Again, I have two bodies. And again, I should say from the beginning, I have actually one body, right, that is moving. But let's say we consider them as two bodies that are initially kind of coinciding. So I have, so what is it then? I have a body, P1 or whatever, and on the body we have again a fixed a frame F1. Okay, so this frame is here, and what the whole thing is doing, it's performing a screw motion about the screw axis. Okay, which means it's rotating about the axis, and at the same time it is translating about the axis until it reaches this place here. I mean, it looks now very simple, let's go this, but it could be very complicated. Okay, how do you get so what do we know already? We know already how to get the rotation matrix that goes from here to here, right? That's the exponential. So you plug in this E vector, and remember that has to be expressed in the one frame, right? So the E vector expressed in this frame goes in here, we get the rotation matrix. Good. What else? The displacement, this is the thing that is now the new part. How do I get the displacement from here to here? Which is the vector R12 expressed in the one frame. So I'm asking for the vector that goes from here to here, and it's expressed in this frame. So the relative translation. If you look a bit careful, what is it then? And again, the assumption is that for at the beginning, for no motion, F1 and F2 are equal. I mean, they're overlapping. Okay. So I claim this is true. So let's say we have so at the beginning for phi equals 0, for example, this is the beginning. Okay, because you have a screw that is defined by the angle. Right. Yeah. So I claim this is true. Okay. For at the beginning for phi equal to 0, this is the identity matrix. Right. This means it becomes 0. The whole thing becomes 0. And this is of course 0. So essentially this is 0, which makes sense because at the beginning there the distance between this and this is 0. Right. Then I start moving. So what if you split this? I mean, if you factor this out, so what we have here is P minus R times P, right? If you separate the brackets terms. Okay. So P minus R times P. Okay, so what we're saying is that where's P? So P is measured from here, it's here. So this stays fixed, right? Just imagine what happens. So this I minus P, so P is here. So this is measured here and then. So then it starts moving. Then what is this? This is then minus R times P. And this is the current P, right? So essentially this P is moving. I don't know how, but it's just moving. And then of course the difference is exactly R minus what happens when you move the guy. So it's essentially this distance here, right? And this is essentially the distance that these two frames are performing. So essentially that's the simple expression for this. And what comes on top of it is if the pitch is non-zero, if you're sliding along the axis because of the pitch, then this is comes on top of it. Okay, so well, this is just a formula. This is just saying, okay, I have the explicit form for this homogeneous transformation matrix in terms of the pitch, the angle, and the axis. Yeah, okay, so this is it. I mean, not really super interesting. I mean, it is, but maybe it's not where we want to end up. You can do a bit more. You can do, because this is not having any, particular screw theory or something like this. What we could do is, so these are the ingredients. What we could do is we could say we introduce something new. And what we are going to introduce is what we call screw coordinates. Anyway, what it is essentially is saying that, look at this guy first here. Do you know line coordinates? How do you describe a line in space? The different ways of actually describing lines, right? Yeah, different. Yeah. But these are the formulas. But conceptually, I mean, lines can be. Yeah, that's difficult. This is a very simplified version. You take 2 points, then you say, okay, the line goes in there. Mathematically more, let's say, solid is like intersecting planes, for example, right? So this is one thing. But if you really go into geometry, you will always find this kind of line coordinates, or they call it Plücker line coordinates. Essentially, what you align, let's say this is our line we're interested in. Now, this axis is a line. So first of all, you have to know the direction, right? So that's why we need E. So we need the direction. Okay, this is one thing. I know the line has a certain direction, but I don't know where it is. So where's the line? And that's, of course, where we need the position on the line, right? So I need to point on the line to say, okay, the direction is E, and the point is here. Then I know somehow where it is. The thing is that this description, when you really use just E and P, is not invariant because it really depends on the point. Because if you take a different point, then you get a different line, seemingly. And that's why, there's a bit more behind it, but that's why essentially they use the cross product. Instead of saying, okay, our information about the line is E and P, they say, no, it's E and P cross E. Okay, why? Or what's the benefit? Well, the benefit is that this is independent of the point. Okay, what do I mean? What if I change the point? So let's say this is all this makes sense, okay? What if I change P? When I say I change P, what does if I pick a different point on the line? What does it change? So how does this term change when I change the point on the line? Or does it not change?
The magnitude would change with the direction.
I'm not sure. Are you sure? It's the cross product, yeah. Okay. P and E. Okay, so let's say we have this. Let's say we have this P. So this formula. So we have this term P cross E. Right? By the way, in our new notation, this would be P tilde times E. Right? Just to remember. Anyway, so now I change from P to, I don't know, P prime, for example, which is P plus A. No. So when I say, okay, so what does it mean to pick a different point on a plane, to pick a different point on a line? It means that I start from P and then I go along the line, which means I somehow have to add the unit vector E, because this goes along the line, plus a certain, I don't know, scalar, right? Because this, by fixing A, alpha, you go along the line. You start from P and then up and down wherever you go. So how does the cross product change? Oh, it doesn't, right? Because now you would have P plus E. I'm sorry. So you would have this one. So from here, from here you get this. You get P cross E plus alpha, and now comes this one, E cross E. And what is this? Come on, guys. It's 0, exactly. So it doesn't change. And that's why they like to use this cross product instead of the P itself, right? So you use the E and the P cross E. What does it have to do with us? Let's see. And this is, they are called line coordinates, or sometimes called Plücker line coordinates, right? Yes, but you see that there is this extra term which has to do with the screw, with the pitch, because a screw is something different from a line. Okay. Okay, good. There we are. So no, this is the wrong thing. That's nice. So we have a formula for expressing this, but okay, we are going to use this formula for computations, but we are going to introduce a different formula for derivations when we have to derive some formulas. Yeah. Okay, we know this. Okay, so this is this. Yeah, I'm not sure why I have it again. So essentially, you have this, by using this formula, you have the screw motion that we are looking at. Yes, so we have this screw coordinates. So the whole 6 vector we call screw coordinates, okay? That are supposedly describe the screw motion of our rigid body. What we could do, because this is 6 vector, what we could do, we plug this into a bigger matrix. And we plug this into a 4x4 matrix. Okay, what I'm doing here is, as you did before, I take this vector E, and I plug it into this skew-symmetric matrix E tilde, right? And then I just copy this vector into here. So from the far distance, just to see, this is a 4x4 matrix, okay? This is a 3x3 matrix, and that's just a 3 vector. So 3 times 3, so to say 3 times 1, this is a scalar, and this is a 1 times 3, 0. So the whole thing is just matrix and vector, and the rest is 0. Okay? And now the same claim that I had before I can make for these matrices, saying that if I plug this into the exponential for the matrix, what comes out is is our homogeneous matrix describing exactly this screw motion. And that's almost full stop. And that's what's called the exponential mapping, or the exponential for rigid body motions. Okay, if you are lost now, that's okay, because there's a lot to take in. There are 2 messages here. This formula is the one that we are going to use for explicit computations, in our course at least. That formula is good to know. Why is it good to know? Why is it good to know? Yeah, why is it good to know? Instead of time. What we're going to do is to look into kinematic chain again, right? Now, if I know that, so what did we look at? We looked at the motion of 2 frames. So one, or let's say 2 bodies, right? The one, F1 and F2. And they are performing a screw motion about a certain axis. Now imagine that you have, for example, again, the simple case of a revolute joint. So you have link 1, link 2, and they're connected by a revolute joint. So the relative motion due to the revolute joint would be exactly this H12, right? So the H12 would give you the relative motion of the 2 bodies in the chain connected by a revolute joint. Right. And now what we know is that this can be expressed in terms of an exponential. Because when you have a kinematic chain, right, we have like for the robot, it's this kind of standard industrial robotic arm, we have 6 of them, right? So what you would do, you would say, okay, all together I have to have H12, followed by H23, followed by, and so on, right? Maybe 3, 4. Okay. And now symbolically, not only symbolically, mathematically, if you use this, for example, what we're going to end up is a very compact form saying that this is x of phi1 x1 hat times, there's no space here, x, okay, you know what I'm talking about, right? x2 and exactly this. So, it's too vibrating. Stop. Okay. So essentially what I'm saying is we can express the kinematics of a robot or a kinematic chain by multiplying these exponential functions. And they have an explicit form that is shown at the top. Okay, what else is, why is it so good? I mean, why is it so beneficial, so to say? Is it just, a bit more mathematics, or is it really giving you some more insight, and does it make life easier? And that's what we're going to explore very soon. One benefit. What is? I don't know if you realize this. What is one benefit? I was actually kind of nagging on the H parameters. So when you, for example, have that motion here. Anyway, this one. What are the DH parameters for this? Well, you know how to do it, I guess, right? I mean, so there's let's say we have a rotation. Yeah, I don't know. Let's say pure rotation, right? The DH parameters also account for pitches, right? For non-zero pitch? I can't remember. Do they? I guess so. Yeah. Anyway, so the DH parameters, so you know how to introduce them, right? Somehow. But you don't have to do it here. The only thing that you need is to measure a unit axis along a unit vector along the axis, and that's it. And then you plug it into the exponential. And what's even better, that's what we are going to see, hopefully, in the course. You can express all these vectors with respect to one single space fixed frame. So the only thing you have to do, you measure all the, you have your robot and you have all the axes, and you measure them just from the space fixed frame. And that's what goes into the exponential mapping. I know the H parameter is nothing. Hopefully this is somewhat convincing. That's certainly beneficial. And the other one is if you look into derivatives like velocities and stuff. Yeah. What do you think is the derivative of an exponential? So if I say I have t times x, for example. Yeah, we will see. But what do you know? So let's say x is constant, because in our case, I guess it's constant. This is something you learn in system theory, I guess. This is actually kind of the fundamental kind of, moments in your study that you see, oh, well, this is all, once you have an exponential, everything becomes easy. So why? Because what is the derivative of an exponential? It's repeating itself, right? So what do you get? Okay. So you are saying it's this, right? Sorry, like this. One more x, like this. Okay. Everybody agrees? Remember, this is a matrix. That's a matrix, and this is a matrix. Matrices don't commute. So which one is it then? Is it, because you could have also said like this, right? Okay, and which one do you believe in? But remember, it's not a religion here. It should be some of them should be correct. That's very good. Try to prove anything. They're both correct. Question why? We come back to this later. But this is the point. So first of all, I mean, the parameterization of the motion is going to be very, at least more easier. And also, when we go to velocities, the thing becomes easier. Okay, then let's start with some other stuff. Yep. And didn't we have this already? I think we had this already, right? Did we? Yeah. Okay, maybe I copied it. Maybe this was too much. Anyway, so no, this we had. We didn't have this one. Yeah. So we have what is it then? We have actually two types of 4-4 matrices now. Back and forth. So the one is this homogeneous matrix, right? So we have the rotation, you know this. So, and now we introduce something different because now we have this kind of 4x4 matrix. And what I'm saying is actually that you get from out of this 4x4 matrix, you get this 4x4 matrix by the exponential. Okay, so we have two spaces now of matrices. Okay, we looked at this one. So we said this is. Did we look at this one? Yeah. And by the way, this is called SE3 because it's the special Euclidean group. So essentially, what it means, because these homogeneous matrices, they perform transformations in E3 in the Euclidean space, right? So frame transformations, so rotations plus translations. So this is what's happening in Euclidean space. And they are special in a sense, again, because we have the rotation matrix is a proper rotation matrix. There's not reflection in it, so the determinant is 1. That's why it's called SE for special Euclidean in 3 dimension. Okay, yes, we had this already. So, and then now we have this kind of matrices here, where we have the skew-symmetric matrix, and we have a vector. Okay. So essentially, skew-symmetric matrix, and then we had a vector. So this was the vector that we got from the skew coordinates. But anyway, so 4x4 vector makes 3x3, and a vector makes a 4x4 matrix. They have special properties. What are the properties here? Well, obviously we have the zeros here. So there's a 0 row, and there's a vector, and here's a skew-symmetric 3x3 matrix. What if you add them? What if you add two of these matrices? You get, again, a matrix of the same type. Because if you add a skew-symmetric matrix, you get a skew-symmetric matrix. If you add a vector, you get a vector. If you get 0, you get 0. That's nice. But also you have a unique 0 element, which is a 0 matrix. So essentially what you have, and now I'll talk about addition, not multiplication, right? When you add them, that's what I'm talking about. And that's why you have a vector space. You have a vector space, so you can add them, and they're all the same type. Okay? And there's a unique 0 element, which is a 0 matrix, and there's a unique inverse, which is the negative. If you take this to negative and add it, then we have 0. And that's why, again, there's a nice name for this. They call it little SE3. So this is essentially the vector space consisting of these matrices. And for reasons maybe we are going to see if you have time, they call it the Lie algebra of SE3. Simply because, and that's the next slide, simply because take any of these matrices, plug it in the exponential, and you get out a homogeneous matrix. That's the only reason. It's not, we don't need to really go into all these mathematical details, but the important point is if you start from here. So you have coordinates, screw coordinate that describe spatial motions along a certain screw axis. Okay? So then you plug it into such a matrix, take the exponential, what you get out is the finite motion, the finite screw motion corresponding to the screw coordinate. Yep, and that's what they do in what they call modern robotics. Yep. Okay, yeah, by the way, they are called sometimes They're called twist matrices. So these matrices are called twist matrices, and also that vector is in our in the current setting, it's a screw vector, but also it could be a velocity, for example, right? And then they call it twist, in the sense that, for example, if you go back here and just look at this one, you can also look at this one. Doesn't matter. It's the same. If you multiply this, for example, with phi dot, what do you get? So remember, phi was the hello? Yeah. So we're rotating about the axis with a certain angle. What if you take the time derivative? So I'm asking about the velocity, actually. So what if you take the time derivative of phi multiplied with x? What do you get? I mean, just look at the components. So you multiply this with phi dot. So you get, for the first thing, you get the vector times phi dot. Any guess what that is? So E is the unit vector along the axis about which we're rotating. So the rotation axis, so to say. And now you multiply it with the rate of the, I mean, the time derivative of the angle. So actually, this is the angular velocity, right? So this gives you, so this times phi dot gives you omega, so to say. Omega, the angular velocity. Kind of, hopefully, is okay. What about the second term? And maybe just look at this term first. If you multiply this with phi dot, what do you get? I mean, yeah, sorry, the second term here. What do you get? Of what? It's nice to have the AC on, but on the other hand, it's I can't hear you. Okay, so what do you say? Of the target point. Which is the target point? You mean here? That's a very good guess. Unfortunately, it's not correct. Okay, let's look at the term P cross E. Okay, and you take this times phi dot. Right. We can actually say something because we already said that E times phi dot is omega. So this is already omega. What is P cross omega? So look at this one. So we have the frame. That's our frame. And now we have the vector P pointing here somewhere. So this is P. Then we have omega. Omega goes somewhere here. Omega goes... Anyway, omega is a free vector. It can go anywhere. But let's put it here. So this is omega. So where is P cross omega? I only hear the AC, sorry. The air condition, yeah? Huh? Yeah, so P, oh yeah, right. P omega, so P cross omega, which one? Maybe it helps if I put the omega here, because it's the same, okay? What is it? P cross omega goes outside? Outside, very good. Yeah, I can't write. Anyway, yeah, it goes outside. Okay. The question was which of what point is it actually the velocity? So he was saying that this is the linear velocity. I mean, let's say the cross product is like this. This is P cross omega. Or maybe it comes out, right? Oh, someone likes... No, the question is it the velocity of this point or is it the velocity of this point? Of this one? I don't know. I would say it's the velocity of this point. Why? Why?
We also consider the V, right? So
Mm-hmm.
we're actually measuring how much that point has traveled along the space the translation. We're not just considering the axis.
Mm-hmm. Okay. If you say so. Oh, wait. So can I just, because the other part would be h times e times phi dot. No, this one. Huh? What about the other part? Plus h e phi dot, which is omega. What is this? The translation of along the screw axis, right? So altogether, you have this cross product translation. I mean, that's essentially translation linear velocity due to the rotation plus the one that goes because of the translation along the axis. Okay. Yeah. Oh yeah. So I'm actually came to this, and that's why it's called sometimes called twist matrices, respectively twist, because the question is how do you call omega, and if you say the linear velocity, right? This is the sixth vector, and so this is omega. I mean, this is the angular velocity, the linear velocity, and the thing is, how do you call the whole thing? And they call it twist for some reason, or sometimes velocity screw. I mean, there are different names. Twist is what you most of the time find, but they also call it velocity screw. Yeah. Mm-hmm. Yes, and in the most literature you see first omega and then the linear velocity, as we did here. In the kind of European literature, it's sometimes swapped, so you have to be careful. All right. I guess I have a tea here. So let's have a 5-minute break or something. Oh no, it's almost done. No, forget about it. No, we don't have to break. It's 50 minutes left, right? Oh, it's okay. It's okay. No, good. Yeah, so we are there almost. Maybe just again. So this we had before when we talked about the combining elementary motions, right? And you said this gimbal lock stuff and so on. So when we have combined, x, y, z rotations or whatever combinations you want, and then it goes essentially like this: you combine again, as I was saying, for the full motion, you combine these rotation matrices, which means the exponential mapping, and so on and so on. It's not important. Yeah, and you do, of course, the same with the full motion. And we are not really using this kind of things, but just for completeness. Now you have this 6-vector space, right? And in the 6-vector space, you also have the basis vectors, right? So you have the with the convention that we have first the omega vector and then v. We have here the basis for the rotations and here the basis for the translations. And essentially, this would be like a pure x rotation. This would be a pure x translation. And if you plug it into the exponential, you get exactly what you want. And as you discussed, you see exactly this is the rotation about the x-axis, and this is just going along the translation along the x-axis. Yeah. And by the way, I mean the thing is that we have always used we have this variable phi, right? But if it's a pure translation, we don't normally use phi because phi should be an angle. But anyway, it's just a parameter. Okay. Yeah. What else do we have? Yeah, this was an example, by the way. Let's maybe have an example. And the example goes like this. I would like to. So this is the example. So we have I don't know what we're having here. We have a beam here, like a slender, I don't know what, that is rotating about this axis. Okay, so and at the end of the beam, we have a coordinate frame. And I would like to see the exponential that describes the rotate, no, the full motion of that frame. So the homogeneous matrix that maps from here, from the terminal to the initial point position. Okay, let's see. So what do we need? What's the ingredient here? So we need the unit vector along the screw axis. We need the point, a vector to a point on the axis, and then we are there. I mean, we all have all the ingredients. Okay, so what is E? So the rotation goes about the z-axis apparently, right? So I guess, yeah, I guess the other way around. Yeah, so E is 0, 0, 1 because we're rotating about the z-axis. The vector P, I already indicated it. So it goes from, we measure the axis from the origin. This is the vector P. Let's say this, the beam or whatever it is has a length of L. Yeah, L, yeah. Then it's displaced in the, I mean, this point, okay, let's go. So this point has minus L in the X component because we go minus L and 0, 0 in Y and Z, okay? And that's almost it because then we just need to compute the capital X vector, the screw coordinates. And then, yeah, so the first component, or I don't know, one component is this, because E is clear, E is, well, I'm always confusing here. So E is, of course, E. And then the cross product is, yeah, this cross this is this. Okay? The pitch is 0 because, yeah, because it is. I just claim it's a revolute joint. And then we have, in the end, we have that this is the screw coordinate vector. Okay, and then you can plug this into the exponential and you would get something. And as I was saying, the exponential we can express, but let's have the explicit form that we have here. And again, rotation matrix, plug it in here, you get the rotation matrix about the z-axis. It's actually wrong. This should be here. Sorry, this is the wrong copy. Anyway, this should be about the z-axis. And then we have this, the displacement vector R. The formula was like this. So we have P, we have to compute I minus R is here, times P, and then we get this. And there we get the correct answer, hopefully. Yeah, I mean, it's just computing it, multiply this, and then you get this. So essentially what you see is we get here the displacement vector when you move along this, I mean, when you do the rotation. And this is the displacement from here to here. And of course, for 0, I mean, for phi equals 0, this is the identity, and this becomes 0. Yeah, not much to say, I guess. We could do another example, which is, for example, come back to this mobile system. So the basic idea here was, of course, to have a, the robotic arm mounted on a mobile platform. That was the idea. Yeah, but I'm just looking at the first one because the question could be asked, okay, what is it's called forward kinematics of a robotic arm, which means you have to compute the pose of the end effector. The pose means there's a frame attached at the terminal end. Okay, and the forward kinematics is the question of us is to answer the question: what's the frame, the pose of the frame, the end effector frame, relative to a reference frame, let's say a space fixed frame, because this is mounted somewhere, could be on the mobile platform or just in space, for given rotation angles. So you get all the angles of the motors, so you know the rotations. And then the question is, what's the relative pose of F7 in this case, because we have 7 joints, relative to this one. So essentially saying, okay, what is H07? If this is F0 and this is F7. That's what we do at the end of the lecture, probably. But a first thing we could do already is to answer the question, okay, what happens in this pose if I turn the sixth joint here. We have 7 joints, 1, 2, 3, 4, 5, 6, 7. Anyway, so what happens to the end effector if I rotate the sixth joint? So what I need is the axis and a point on the axis. And that's easily done because, so first of all, of course, I made this a bit easier. So let's say, what's the rotation axis? And it looks a bit skewed, but it's supposed to be along the x-axis. Okay, so the no. So the vector is about the unit vector about the x-axis, which is 1, 0, 0. Yeah, there we go. So this is the vector that goes along here. Then we need a point on the axis. And I would claim that we can use just the point. We measure the height. So the height is the length of this one is L1, L3, L5. So altogether is L5, L3, L5. 1, 3, 5 along the z-axis. And you don't have to care about the xy motion. So that's why we use p equals 0, 0 and this. And then in the end, I mean, the rotation axis is like this. And then you plug it in here, and then you get this. So this is actually the full forward kinematics of the robot if you're just looking at the motion of the joint number 6. Yeah. And that's the position of this origin. Tell me if it's too much, too fast, too whatever, too much nonsense, then I stop. Do you have any kind of questions or so?
In this robot, other professors are not considered, or only other parts are fixed, only this part is rotating?
Yeah, for the example. Because otherwise we are not there yet.
Yeah, because there would be a large kind of equation.
Oh, no.
Everything will rotate.
That is hopefully on Friday. Hopefully on Friday we understand how to model the whole system. Yeah, this is just as an example. Let's say we are looking at what happens if you turn the 6th joint.
I think it is very easy, like a simple approach as compared to the other method. Yeah, I find it like this. Yeah.
That's what.
Straightforward. Any question?
Everybody's sleeping.
So is it good or not?
Shall I go before you answer? I know it takes time to get into it, and if you're bombarded with this, and in 1 week, I'm not sure if you go to dynamics, but let's see.
We have a lot of things to cover, but if as per your absorbed power, we will see how much we can cover.
There's no party tonight.
So, with this, thank you very much, sir, for session, day 1 with all 3 sessions. So, I hope the participants thought or understand something about it. And already we have shared one document, okay, regarding the parallel robot. The professor is given it to me, and I have already shared with you. Those who have not participated yet or registered yet, I kindly request to please register using the link. You can find the link through Ritvik or Sunny Saurabh. So he will give the Google form. You please fill it, okay, and then complete the registration process. Okay, according to the registration, I had to print the certificate. Okay, and I had to get the signature from head of the department or HOD and the director and local guy coordinator. So I had to print it and take the signature. It took time. Okay, so better those who want to register it or those who want to confirm it for next 4 days, they have to register on that and write properly your name. If it is not printed properly here, you can also see in this. If it is not properly printed or not is properly written, then you please write it properly. And those who have registered, like they have written their name, na, only. So they have to register through the link. So I can find their information. Okay. So by today itself you have to complete. And otherwise you don't blame me that you have not given me certificate. This is up to you. Okay. And at the last day you have a exam. Okay. So that exam it is not like that the exam would be taken and you will not get something. It's like a complete grade sheet. Okay. 1 credit course. This GAN course is like a 1 credit course uh, kind of thing. Okay. So you will get a complete grade sheet like you are getting for BTech or MTech. Okay. Similar kind of thing here. After completion of your course, after examinations, whatever mark you will get, some grades are there, AA, AB, AC, AD, like this. So based on that, you will get your mark. Okay, a grade sheet would be provided to you apart from certificate. So don't